Hi, this is Subhashini, and today we're here to talk about linear regression. Now, you might ask that linear equations, linear regression, these have been part of our lives since maybe class 8 onwards. So, what is so unique? Why are we dedicating so much time and effort into this type of a predictive technique? And the answer here is that yes, linear regression and linear equations are things that we know, but the use and the way we work with it differs on the type of data that we are going to be working on. Now, here I am going to take you through 4 case studies. The first one will be on a small set of data where we need to create a bigger sample just for the linear regression to be statistically correct. Then the second is for summarized data across a variable. And the third is for a large data set. And the fourth is for unstructured data in an ML model. So yes, we are going to look at linear regression, and it's going to be extremely interesting because we are going to look at it in terms of different types of data. Let's start with the first case study, linear regression, where we have a small data set and we need to create a bigger sample so that we can come up with the right kind of takeaway. You have seen some case study that I have created around this earlier on the channel. This one is to give you a perspective of linear regression with the types of data available. So, this is my problem statement if in the form of defining it for the data available. I have a small set of data, but what I really would want to build a linear regression on would be something like this, much more data. Okay, that will give me the confidence that I can go ahead and use that linear regression in the long run with the organization. Now you might say, why do I need larger amount of data, and can the organization not wait for the data to come? So yes, of course, there is one thought that the organization can wait for the data, but that would maybe the growth rate is so less that it would not suffice in the very near future. So you would actually have to shelf out your analytics, saying that we really can't do this just now. Okay. So a good way is to oversample and make it into a larger set of data. Before we get into that, let me just touch upon the fact of correlation. As you know, the relationships between the x and the y variable, the first level of relationship can be understood by correlation. And both these slopes on the screen here show 100% correlation. However, one slope is uh, with a -1 correlation. That means as the y variable increases, the x dips in the exact same amount, while the one on the right is with a positive correlation. That means as the y increases, the x moves in exactly the same amount and vice versa, right? So both these relationships are perfect correlations. What exactly is it that we are trying to create? We are trying to get this best fit line, right? And what is this line of best fit? It is the line where the overall error term for the distance between the various y variables to this line is minimized. So we know that in a linear fashion, if I could take this line upwards or increase this on any one of the sides, it would be the best predictor of the y. So here I have the data in Google Colab, and the great part with Colab is that my data is in the drive and I can just import the data in. I know you've seen the earlier video where details of the code have been shared with you. So I'm assuming you know how to work with Google Colab. So when I bring in the data, what do I find? I find that the data has 6 columns and just 20 rows of information. So this is a small company, okay? And it wants to know that what is it that affects its employees' satisfaction score. Being a 20-member team, 2 or 3 people are added into the team and 2 or 3 people exit the team every year. So the rate of change is very slow. Okay. So let's understand the data a bit. As you know, we will be looking at the DECOVA and I process where we define the business problem, collect the information from various data sources, analyze it, and finally come up with insights. So here it is on the screen in front of you, the DECOVA and I process. We start by defining the business problem. The problem is that this is a small organization and it wants to understand what drives employee job satisfaction score. So the Y variable is the job satisfaction score, which is a static score between 1 and 10. The data has 20 rows only, one for each employee. And there are 6 columns that we spoke about just earlier. Employee ID, department, tenure, age, job satisfaction score, and training hours. There is no extra data set given. So in collect, there is no extra step. In organize, we will go through all the 4 steps. Missing values. So here we have no missing values. How did we know? We had run a df.info here, if you'd see, and there is just no missing values up here. All the values are not null. Outliers, the Y variable has fixed values. There's no outliers. Dummy variables, the department is a data object. That means it is not numerical and we will need to do dummy values there. And then we have derived variables, which we will see. Do we need it or not? Okay. Then we look at analyze. So the two big statistical analysis here is going to be correlation and the linear regression. Correlation will tell us which are the relationships which are significant, and linear regression will find out the exact significance of the relationships which matter. And then finally, we will look at the insights. Now, one easy method to do a univariate analysis is to use the SweetWiz library. You've again seen it in an earlier video. So I know that you know how to use it. And once the univariate is done, what we do is do a bivariate analysis. Now, how do we do the bivariate analysis? We can do it with a scatter plot. Okay. For the job satisfaction versus training hours, job satisfaction versus tenure, etc. Okay. So a bivariate analysis is very easily done on the basis of a scatter plot. And then we want to move into the correlation. So here you can see we have done df.cor, and only for the numerical variables, we want to run the correlation. So I have done numeric underscore df .cor, right? So when the data for the numeric variables, which are employee ID, tenure, age, job satisfaction, and training hours, does not include department. When the correlation is run, we get a heat map. Now this heat map we get with the help of the two visualization libraries, Seaborn and Matplotlib. Okay, so here you go. We can see from this that the highest correlations and the lowest correlations are marked from blue to red. Okay. Any value with itself is 100% correlated. By this logic, you can see that tenure is very highly correlated. 1 minute. To the training hours. Okay, so here is employee ID, tenure, age, job satisfaction, and training hours. And so also here, employee ID, tenure, age, job satisfaction, and training hours. So if I look at job satisfaction, it is highly correlated to tenure and age and training hours. So these are the most important ones. Truly, it should not have been correlated to employee ID because that's a randomly generated ID, and true enough, there is no correlation to employee ID. Okay. Now here, we had already spoken about the fact that in the course of things, we would want to create a dummy variable for the department. So we are going to use the get dummy code and run out the dummy variable for the department and then drop department. Okay. Now, see, there are different ways to calculate correlation. The most common ones are Pearson, which is suitable for normally distributed data, large data sets. Spearman, which is used for ordinal, interval, or ratio data. And what is the type of Y variable we have here? We have specific values, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay. Chi-square, which is ideal for categoric data to assess the association between the categories. Now here itself, we are declaring that the size of the data set is small. So one of the things that we will have to contend with is the small sets of data, especially if we are looking at HR for smaller organizations, or we are looking at B2B businesses where the count of customers is less, but the value of the ticket size is large, or if we are looking at medical exigencies, like cancer, etc., where a particular scenario will come very few times. Okay. So all these places we will find data which could be quite small. So what is the solution here? We'll make a model with the existing data, the small data. Check. We will also create a large data set, a big data set. Check if the big data is similar to the small data so that it is a good representative of the data that we actually have, and then recreate the model on the big data, and finally we'll compare the two models. So this is the methodology forward when we have small data sets. Okay, so let's rerun the correlation. First thing that we have done is that we have created the dummy variable. Now we have more number of numeric variables, and we rerun it with Spearman. Okay, because we know that our Y variable is graded. It is between 1 to 10 only. Okay, so we run the data, and then of course it's always easier to visually understand it by taking a pictorial representation. So here is the heat map. Okay, again, when we look at job satisfaction score, and we want to see which are the values which are important for job satisfaction score. So it is the first, second, third, fourth item, first, second, third, fourth item, this column. Okay, 0.02 onwards. So what do we find? That even now the tenure, age and the training hours are by far the most important variables. Okay, so creating the extra dummy variable for department has not changed anything much. Okay, so now how do we create the regression equation? The practice is pretty simple. We divide the data into training the model, and then testing the model, and then we find out the equation. So here is what we've done. We have taken the data, and we have created the model X train, X test, Y train, and Y test. The test and train has been split in 0.2, which means that 80% is for creating the model, testing the model, and training the model, and 20% is for testing the model. So you can see test size is 0.2. Okay, so we'll go ahead and run this. And what do we find? We find this is the mean squared error value, and we find the coefficient of each of the x's that the model has used for the calculation. Now, obviously, this makes it a bit difficult for us to interpret. So what do we do? We just display the equation. Okay, we ask the system to display the equation, and then we can see 0.07 into tenure plus 0.12 into age minus 0.01 into training hours plus 0.34 into department IT. So you can see that the equation has been created. At the really at the end of this equation, you see 3.48. This is the intercept value. Okay, this is the minimum value if all these values were actually zero. So if training hours is zero, department is zero, etc. Everything is zero. Then also the job satisfaction score was standing at 3.48. Okay. So then now that we have created the equation, we want to test it and then form the confusion matrix for ourselves to understand. Now here you'll see R square of the train and the test, adjusted R square. They're looking pretty way off each other. Okay, not a good model. Okay. Then we also want to just check out how it looks, the equation looks visually, and here you get the equation to be seen visually by just doing a plot. Again, you have Seaborn and Matplotlib. Okay. So go ahead and use these libraries to um, do the needful. Now here you will see that, it doesn't seem that it is a great idea to go forward with this model. The sample set is very small. You need at least 30 data points, right, for a normal distribution to occur, and we are below that value. So what do I do? Because we have a data which has a few x variables, I take a n value or the count of the new data that I'm trying to create as 1,000. And with this, you can see over here with random sampling, I am creating a larger data set. This is called big DF. Okay, this data frame is called big DF. It mirrors the values in the small data frame or the original data frame. Okay. And then what do we now? Obviously, we've made this new bigger DF. But one thing we want to be sure is it close to the original data? Because in the real world, we're not doing an academic exercise, right? What we want to do is we want to know, is it close to the real data? So here you go. I say that there can be a 10% difference. It should not be more than 10%. There has to be a 90% similarity. And a brief calculation tells me that, let's see here, big DF and numeric DF are similar within the specified threshold of 10%. Okay. And if I want to look at every variable and check also, you can see the percentages. You can see some places where it is, very, very small, right? It's 0.9%. So these are whole percentages. The largest seems to be department sales at 9.5%. Okay, that's the place of the largest divergence. Okay, so what have we got now? We have got a large data set, and we would want to run the same linear regression model now for the big data, which is called big DF in my code. You can name it whatever you like. Why do we want to do that? We are now assured that this big DF mirrors the original data, and we want to build a more robust linear regression equation. Okay, so how will we do it? We will make the equation on this big DF. We will reuse the code. And then at the end of it, we are going to compare the R square and the adjusted R squares of the two models and see which is higher. I can tell you, and I think you would also have figured out by now, that of course, big DF would have a more stable model, a better R square and an adjusted R square. And this would be a great method for us to create a working model for this organization. With this, I'll close this session. Do reach out to me for any queries that you may have. In my next demonstration, I will show you how to create a linear regression equation with summarized data. Okay, then see you soon.